All right, guys. So the first thing we're going to do, we're going to start with one problem. And in this problem, we are given capacitor value. We are given current or voltage passing through a capacitor. And then we are going to calculate um, our voltage across the capacitor, and we will calculate current passing through the capacitor. We are going to calculate the power dissipated in the capacitors, and then we are going to calculate energy stored in the capacitor. So one problem we are going to use to calculate multiple items that we discussed last week. Let's go ahead and do that. Let's call this our problem 1 for today. So we have a capacitor. Current is flowing through the capacitor. Of course, current cannot flow through the capacitor as we discussed, but it's just a figure of speech. Capacitor value is 0.6 microfarad. And the voltage across the capacitor is given. Capacitor is initially resting or it is not charged. That means capacitor voltage is 0 at time less than 0. And then capacitor voltage is 40 E negative 15,000 T sine 3000 E volt for time t greater or equal to 0. Now, one thing we discussed last week, or not last week, on Monday, that capacitor voltage cannot change instantaneously in an instant of time, but the capacitor current can change instantaneously. So one thing that we used very commonly in when we are dealing with the capacitor voltage is we use the symbol zero, zero positive and 0 negative. So time is equal to 0 positive and 0 negative. That is, 0 negative time means that if your circuit is, you have switches in the circuit or any change is happening in the circuit, that circuit also has a capacitor, then the capacitor voltage just before the change is happening at time t is equal to 0. So 0 negative means just before 0. That voltage across the capacitor is not going to change just after the change is going to happen at 0 positive. That that is to represent that capacitor holds its voltage and it does not change in an instant of time. So anytime we are dealing with capacitor voltage, we will always assume that just before a change is happening in the circuit and capacitor has to reorganize its energy to go from one voltage to the other voltage, that is going to take some time. And the change, when the change is happening just before the change and just after the change, the capacitor voltage is still going to be the same. And we can observe that from this equation as well. Capacitor value is 0 at t less than 0. And then capacitor value is given by this equation when t is greater or equal to 0. So if you look at that, if you plug in t is equal to 0 in this equation, of course, sine of 0 is 0. So this whole thing is going to be 0 at t is equal to 0 as well. So the capacitor voltage is going to be 0 at t is equal to 0 negative, and it will be 0 at t is equal to 0 positive. That is, it will hold its value of 0 and then it will start changing. So we are going to use that notation of 0 positive, 0 negative, or in general, t positive and t negative. T positive means if something is changing at t or t naught or whatever you want to call that time instant, just before that time instant and just after that time instant, the value of the capacitor voltage, we will assume it will be same, it will not change. And we're going to use that when we are discussing RC circuits. Okay, so what we have to do in this one, the first part is we have to determine the capacitor current at t is equal to 0. I can call it 0 positive, but let's just go ahead and do it 0. All right. Yes. So 0 positive means just after change is happening. 0 negative means just before the change has happened. Now, since the voltage was 0 at t less than 0, capacitor is assumed to have no energy stored, and generally there is no current flowing through the capacitor, right? Now we want to see if the current is going to change instantaneously. Like we saw that last on Monday, when we solving a problem, we saw that the current did change instantaneously, but the capacitor voltage was taking its time to change. So basically at t is equal to 0, or you can find current at any time, but the reason we are trying to find the current at t is equal to 0 is to again see, since the capacitor voltage is still 0 before t is equal to 0 and after t is equal to 0, if the current is going to change. Before t is equal to 0, current is 0. And now we want to see at t is equal to 0, if the current is going to change instantaneously, it will acquire some value or it will still be 0. Basically, that's what we want to see right now in this first part. Anybody remember what is the relationship between the capacitor current and capacitor voltage that we discussed on Monday? Yes. Very good. IC is equal to C times derivative of the voltage across the capacitor. So we're going to go ahead and calculate the value of IC for t greater or equal to 0, and then we will plug in the value 0 to figure out what is the value of current at that instant of time. So IC is equal to C d over dt 4t e negative 15,000 t sine 3,000 t. I'll take 40 out, 40c. Okay, who's going to tell me derivative of exponent negative 15,000 t sine 3,000 t? What will be the derivative of that term? Okay. No, yeah, what will be the derivative of this? Okay. And then there will be another term with that, which will be 15,000. Negative 15,000, yeah. Because you are going to take the derivative, so e to the power x derivative is e to the power x, but e to the power ax is going to be e to the power ax and the derivative of ax. So in this case, you're going to have negative 15,000 e to the power negative 15,000 t sine 3,000 t. All right, what else? Plus? Okay. Okay. And? Okay. So I'm going to put 3,000 first. 3,000 e to the power negative 15,000 t cosine 3,000 t. So this is our derivative of current. We don't really need to do any further simplification because all we need to do is to put t is equal to 0 in this term, and we can figure out what is the value at t is equal to 0. Now, we know that some of the terms are going to be 0. Sine 3,000 t, when you put t is equal to 0, this term is going to become 0. So we can simply 0 at t is equal to 0. Cosine 3000 t, cosine 0 is 1. So this is 1 at t is equal to 0. So basically, we have to figure out what is the value of this term at t is equal to 0. So e to the power 0, 1. So this is also 1. 1 at t is equal. Of course, you can put your, in MATLAB or calculator, but these are simple things. There is no need to put all, everything in the calculator. So basically, you will end up with IC at 0 is 40 times C, and this is 0, this is 1, this is 1, and you're gonna have 3000. 3000. All right, let's see. Capacitor value is given as 0.6 microfarad. So 40 times 4 threes are 12, so that's going to be 12. 40 times 3 is 120, so 120,000 times 6 microfarad. 6 exponent negative 6 times 4 threes are 12, 12 exponent 4, right? 12 exponent 4. 12 6 are 72, so that's going to be 72 exponent negative 2. 72 exponent negative 2 ampere, which will be what? I see 0 is, if we do, so that's going to be 0.72 ampere, or 720 milliampere. I'm just want to confirm if we are doing it. So 3000 times 40 is 12 exponent 4. 4 times 3 is 12, and then we have 4 zeros, and then 6 exponent negative 6, right? Oh, 0.6 exponent negative 6. Sorry. So we have 0. This? Well, this is 0. This is 0, so whole term is 0. That's 0.6 micro, not 6 micro. So that's going to be 7.2 exponent negative 2, or 0.072 milliamp, right? Or 0.072 amp, sorry. 0.072 ampere, or 720 milliamp. Or 72 milliampere, sorry, not 720. Okay. So this is 72 milliampere is the result of the first one. So remember one thing, when a specific value is required at a specific instant of time and you have an equation, you don't really have to spend time on simplifying that equation, because in that equation, first of all, many things may become 0, or even if they're not becoming 0, you can just put that equation in Octave or MATLAB without simplification, because simplification is going to take time. So just put that equation in MATLAB, put t is equal to whatever value, and then it's going to give you the result. There's no need for simplification in that case if it is not required in any class, basically. Now, if it is required that, yeah, you have to give the simplified result, then yes, you have to go and simplify the equation to give a simplified result. All right, second part is, what is the capacitor power at capacitor? At t is equal to, let's see, pi by 80 millisecond. So the capacitor power is calculated, of course, as the product of the capacitor voltage and capacitor current. And then we did the derivation of this equation using capacitor voltage or capacitor current. So in this case, the current equation is C dV over dt. So our final equation is CV dV over dt. Now dV over dt, or the current expression, we just did the current expression, which is right over here. This is our current expression, IC. And V, we already know what V is. So we can calculate the capacitor power, or we can first write down the capacitor equation. V is 40 e to the power negative 15,000 t sine 3,000 t, and then our expression for I that we calculated is 40C, and then this expression. We put 40C outside. 40C, and then negative 15,000 e to the power negative 15,000 t sine 3,000 t plus 3,000 e to the power negative 15,000 t cosine 3,000. So this will be the expression for the capacitor power, voltage times capacitor current. Yes, there is. Yeah, current. So that's pretty much what we use for any calculation of any power, voltage times current, right? Voltage is given to you. That expression is given to you for t greater or equal to 0. Right? Yeah, yeah. So that expression is 40 e to the power negative 15,000 t sine 3,000 t. All right, so now again, don't need to simplify anything. We need to find the power at a specific instant of time, and that's what we are going to do. Therefore, capacitor power at pi by 80 millisecond, and we're going to go to our Octave or MATLAB, whatever you want to use. Okay. So my time is pi by 80 times 1 exponent negative 3 millisecond. My capacitor value is 0.6 micro. And my capacitor power equation is 40 times 40 times e exponent of negative 15,000 times t times sine 3,000 times t times 40 times c times negative 15,000 times exponent of negative 15,000 times t times sine 3,000 times t times, or plus, sorry, plus 3,000 times exponent of negative 15,000 times t times cosine of 3000 times t. All right, let's make sure that we are not missing any parentheses. 40 exponent 15 negative 15,000 t times sine 3000 t. So we're missing some, yeah, we are missing some parentheses here. Oh, we're missing one parenthesis here actually. Exponent negative 15,000 times t, and then sine 3000 t. So there's another parenthesis that, oh, we don't really need to put parentheses over actually, because everything is multiplied. 40 times this times sine 3000 t times 40 times c. We need parentheses here because two terms are adding together. So negative 15,000 times exponent negative 15,000 t, there should be parentheses here, times sine 3000 t plus 3000 times exponent negative 15,000 t times cosine 3000 t. Okay, that looks good to me. And again, we are balancing this parentheses with the negative 15,000. This is done, this is done. I think it should be okay. All right, here you go. So 0.042287. Let's go ahead and copy this thing. Yes, Chris. Because the time is pi by 80 millisecond, right? Capacitor at pi by 80 millisecond. Yeah. I think this is one of the problems given in the book, if I remember correctly. Okay. So your capacitor power is 42.247 milliwatt. 42.2 milliwatt. At that instant of time, this is how much power the capacitor has. And calculation is there. Part number 3. Oh, by the way, let me go back quickly. So again, to emphasize about the capacitor voltage cannot change instantaneously, but the capacitor current can. Observe. In the first part, the capacitor current at 0 second is 72 milliampere. So it went from 0 to 72 milliampere in an instant of time. The capacitor voltage is still 0, but the current did change quickly. Because remember, current depends upon the movement of charges. As soon as any charges start moving, the current values start changing. Right? So the capacitor current can change instantaneously, as you can see in this problem and the problem that we did on Monday. All right, part number 3 is what is the energy stored in the capacitor at the same time? Energy is stored in the capacitor at pi by 80 millisecond. Yes, sir. Question? I'm sorry? Yeah, for energy, what is the formula that we used? Okay. So energy or work is 1/2 times C. Okay. So the voltage of capacitor is square. So of course, voltage is a function of time and energy is a function of time as well. Both of them are function of time. So simple voltage equation is given to us. One half C, and the voltage equation that is given to us is what is that? 40 e to the power negative 15,000 t sine 3000. Yes. So let's go ahead and plug in the time value and calculate the energy stored at that time. So W is equal to, all right, so that's C by 2. So C divided by 2 times 40 times exponent negative 15,000 T and times sine 3000 square. So I have to put a square over here as well. Okay. Yeah, that's right. This thing is over parentheses. Oh, no, not here. The whole thing. Okay. Starting from here. Starting from here, we need parentheses. Okay, so 2.0406. First, let me write this down. What is the 2.04? What is the unit for the energy? Anybody remember? Joules. So micro joules. This is the calculation. All right. So in this problem, we calculated 3 things. Given the voltage expression, we calculated current. We saw that the current can change instantaneously. We also calculated the power at a specific instant of time and the energy that is stored in the capacitor at the same instant of time. Yes.
If it changed quickly, then we would have a surge like current
Right.
on the capacitor.
If the voltage, if you assume that the voltage can change in an instant of time, then since current is C dV over dt, it's a rate of change of voltage. If the voltage is changing in very small amount of time, which we assume that instantaneously, then dV over dt is going to be extremely large. And if dV over dt is extremely large, that means what? Current is just shooting very large in an instant of time. Now that happens again, as I said, that happens when the lightning strikes on some, you have the ground terminals and stuff, and when the lightning strike, and even if it's not a ground terminal, if it strikes on, let's say, something very tall building or something, then at that instant of time, it deposits such a large amount of charge on that object that your voltage difference between the ground and that object becomes very large. And the current flow is extremely large. So unless you have, and again, the breakers that we have, usually the response type of those breakers is not fast enough as compared to the time it takes for the energy to deposit that charge. And then, so that's why even the fastest breaker generally, you end up burning stuff. And for regular interruptions and stuff, yes, the breakers can handle that interruption. But when it comes down to the lightning strike and stuff, many times actually breakers cannot handle because their response time is not that fast. But yeah, at that amount of time, basically, you can take that as, again, in engineering, we call it an impulse. Impulse means that a signal has very narrow width, but its height is very like it's infinity. That's a signal which is called an impulse signal. Basically, its height is infinity, but its width is almost zero, and we assume that the total area of that signal is 1. So in general, what impulse is if you have a signal like this, a rectangular signal, and it's for some time, and it has some area, it has some height. Generally, we assume that the impulse signal area is 1 because its height is 1 over t, and it lasts for around t amount of time. Now, what if you start squeezing this signal, start making it thinner and thinner? So at one time, that signal, and so height will start increasing because you want to keep the area to be 1, right? So height will start increasing. Now, if that signal you said, oh, it only exists at 1 instant of time. So to make this at 1 instant of time, the height has to be infinity. So that when you multiply the infinite height with that 1 instant of time, your area will still be 1. So that is a mathematical representation of a phenomena that is happening in a quick instant of time and creating a very large amount of change, whether it be lightning strike or any other thing. This is called impulse function or a Dirac function as well, DIRAC. And that's a very commonly used engineering function to represent that phenomena. Of course, we cannot really simulate that function with our equipment because you need the infinite amount of height for that function. That's not possible. But this function, basically, as I said, it represents all those phenomena that is happening. Those are happening in a very short period of time, but they're making a very large change. So lightning, as I said, is one of the very common example of this. And that's why if your voltage is changing in an instant of time, then the rate of change of that is going to be infinity. And that current is just not possible. It's going to burn everything, basically. So even mathematically, you can see that it's not possible for the voltage to change instantaneously across capacitor. Otherwise, the current passing through the capacitor is going to be infinite.
So like a real world application, they're trying to make impulse.
Well, surge protectors, yeah, grounding, of course, that's what we use, that the current will flow into the ground without burning other things. About surge protectors, and again, I said, with even the quickest surge protector time that it takes, or the fuse, it's not as quick as the time it takes for the lightning to strike and deposit it. It's fast, yeah. But yeah, usually surge protectors, multiple surge protectors, basically that one is going to burn, but in the meantime, the other one is going to, because that's what they use in power system. They don't use just one, they use multiple protections. Substation has its own protection, the tower has its own protection. So they use multiple protections. So at least if one thing is going to burn, the other things they're still going to be safe, basically, by the time energy is going to reach to that point. Right? Yeah. Okay, guys. So that finishes up the discussion of the basic capacitor and the equation of capacitor, current voltage relationship of capacitor, power and energy. So I'm going to post a homework set, of course, based on this as well. Then make sure you do that. Now, we also discussed a capacitor connected in parallel, capacitor connected in series, how you're going to find the equivalent capacitor. I'm not going to do any problems based on that. It's the same thing as resistor, just opposite. So what we are going to do now, we're going to start natural or source-free response of capacitors. Natural or source-free response of capacitors. So the idea here is that you have a capacitor in a circuit, and you are exciting that circuit with a DC source. So the function generator, you're not using function generator, AC source or anything, you're just using your DC power supply. So when you excite a circuit that has a capacitor and resistors with a DC power supply, then capacitor starts charging, right? And as we discussed on Monday, capacitor is going to charge up to whatever the limit it can be charged, the maximum amount of charges that can accumulate on the plates of capacitor. And once that is going to happen, then the capacitor cannot accumulate more charges on the capacitor. There's no capacity on the plates of capacitor to accumulate more charges. So at one point, they are fully charged, the capacitor is fully charged. And at that point, basically, since the movement of charges stop where the capacitor is connected, that means the capacitor current, or in that branch where the capacitor is connected, the current drops down to 0. And we say that when the capacitor is fully charged to a DC circuit, to a DC power supply, then it acts as an open circuit. Why open circuit? Because the current flow in that branch just stops, right? A voltage will still be there. Whatever charges are accumulated on the capacitor plate, they will, they will have the energy stored in the capacitor, and they will keep the voltage between the plates, whatever the final voltage is that we have to calculate most of the time. And if you remove the source now from the circuit, and your circuit is still a closed loop, then that capacitor becomes a source because it has energy stored in that. And that capacitor now starts supplying current to the rest of the circuit. That's called the natural response or source-free response of a capacitor. So that's what we are looking at, right? So we're going to start with the discussion of if you have a simple one capacitor and one resistor circuit. Yeah. It's not a dependent source, it's just energy, because its value is not depending on any other current or voltage flowing in the circuit, right? It's just the energy that it has stored. It starts dissipating that energy if there is no other source available, right? And if you have closed loop, important thing is you need to have a closed loop, otherwise it's just going to hold its charge. It's not going to dissipate that charge. Let me put a switch over here. Let's say this switch opens up at a reference time, and usually we call our reference time to be 0. That 0 can be basically the time at which you are making a change in the circuit, and you start counting. Starting that time, you start counting basically later on, whatever time you are calculating the values. That can be T0, that can be 0, whatever, but that's a reference time basically. And let's assume this is a current source, IS, a capacitor, and a resistor. So we usually assume that the circuit is running for long amount of time, long enough that the capacitor is fully charged. And when it is fully charged, of course, we assume that the capacitor is acting as a short circuit. We find the voltage across the capacitor at that time. And remember that voltage, it is holding that voltage. So if the change is going to happen at t is equal to 0, that is the switch is going to open up. That voltage is going to be the same at t is equal to 0 positive, because that voltage was at t is equal to 0 negative that it was keeping. Remember, capacitor voltage is not going to change in an instant of time. Now, since capacitor, resistor, and source, all of them in this case are parallel to each other, we assume that the voltage across the capacitor is simply V. You can call it V, you can call it VC, whatever you want to call it. So when we are analyzing these type of circuits, again, the first thing that we analyze based upon the description that is given to you, how long the circuit is running. If it is given that the circuit is running for a very long amount of time, basically that is to tell you that capacitor is fully charged. And the first thing you're going to do is you are going to go and find what is the voltage across the capacitor when it is fully charged, when the circuit is running for a very long amount of time. That becomes your initial voltage on the capacitor that you are going to use when the capacitor is going to start acting as a source. That is, if you remove the power supply and capacitor starts acting as a source, that will be the voltage, first voltage that accumulates. That is the voltage that capacitor is going to use initially to start supplying current. And then that voltage starts going down because capacitor is dissipating its energy. So it's important to find the initial voltage on the capacitor just before the change is happening. So at t is equal to 0 negative. In this case, let's assume that circuit is running for a very long time, switch is closed. IS is going to be divided into two currents, IC and then IR according to KCL. Okay, so let me ask you this. If the circuit is running for a very long amount of time, capacitor is fully charged, what is going to be the voltage across the capacitor at that time? Same voltage drop across resistor, and that voltage we can calculate as IR times R. IR times R. So the initial voltage on the capacitor, if the circuit is running for a long time, capacitor will be fully charged and it will start acting as a short circuit, as an open circuit. Therefore, no current will flow through the capacitor. All the current is going to flow through the resistor, and the source current is going to be the same as the current passing through the resistor. So IS and IR will be same. At that time, so V will be equal to IR times R, which will be IS times R. And we call this voltage as the initial voltage across capacitor. We call this, let's say, V naught. And the voltage at time t is equal to 0. Now this voltage across the capacitor, as I mentioned, is going to be the same at negative and positive instant of time, just before the change is happening and just after the change is going to happen. So the voltage V naught will be across the capacitor. Okay. Now let's say at t is equal to 0, the change happened. At t is equal to 0, switch becomes open and RC circuit becomes source free. So now we have to concentrate on the source free circuit after the switch gets opened. So you have the capacitor and you have the resistor. IC, IR, capacitor, resistor. and the voltage V. All right, let's go ahead and apply KCL to figure out what will be the expression for the voltage V for time t greater than or equal to 0. KCL, yes, you can call this node A and node. All right, what will be the expression for KCL? IC plus IR equals 0. All right, what is IC in terms of voltage V? C dV over dt. And of course, IR using Ohm's law is V over R is equal to 0. Okay, we'll manipulate it a little bit. So we'll keep this as dV over dt is equal to negative V over RC. We take this on the other side, divide both sides by C. And then we bring V over here and we took dt on the other side, minus 1 over RC times d. And now to find the expression for voltage, we are going to go and integrate both sides because integration is the opposite of differentiation. So integrate dV over V from the initial value V naught to any value of capacitor voltage at time t. Take initial value of time t is equal to 0 to any time t. All right, what is the integral of 1 over V dV? Anybody remember that? Natural log of V, very good. So we are going to put natural log of V, limits are Vt and V naught. And of course, integral of 1 is t, so negative 1 over Rc t and 0. Natural log of V of t minus natural log of V naught negative 1 over Rc times t. Now, if again at the lower limit, if it is not 0 time, if your reference time is not 0, it is t naught, then of course you can just use t naught, and then it's going to become negative 1 over Rc t minus t naught over here. Generally, it is usually easier to take the reference time at 0, but some of the problems we may have two switches changing at different times, so either we can just shift our reference and call it 0 every time the change happens, or we can keep first at 0, the other at t naught, so it doesn't really matter. All right, natural log of A minus natural log of B, we can write that down as natural log of A over B. Is equal to negative 1 over Rc. All right, to get rid of natural log, we take the exponent of both sides. So we take the exponent on both sides. On this side, we will be left with Vt over V naught, and the other side is going to be e to the power negative t over Rc And finally, the expression for the voltage is going to be V naught e to the power negative t over RC. For t greater or equal to 0 positive. You can keep 0 if not 0 positive, greater or equal to 0. So that is the expression to calculate the capacitor voltage in a circuit where capacitor is discharging with the initial charge stored and having an initial voltage difference between the plates represented by V naught. As you can see, it discharges exponentially with respect to the time. And that RC, this constant, that is called, anybody remember what you call this? The product RC. Anybody remember that before I write? Time constant. It's called the time constant. You guys did that, right, in some class before? AC, at least AC. You guys have discussed that AC. Maybe not 2035, or did you discuss? No, but people who took AC, they must have discussed this in AC circuits. It's called the time constant of the circuit and represented by generally Greek letter tau. So we can, in terms of time constant, we can represent the voltage as V naught e to the power negative t over tau. What is the significance of the time constant? Or in general, how do you define time constant? So to define, to understand that, let's go ahead and you can plot this, but I'm just going to plot it freehand. Time and voltage. All right, when time is 0, what is the value of the voltage across the capacitor from the equation? V naught, right? E to the power negative t over tau, t is equal to 0, exponent becomes 1, and the voltage, capacitor voltage is V naught, which we are expecting because voltage across capacitor cannot change instantaneously. So that's V naught at time t is equal to 0. Now, one time constant, that is when t is equal to tau, right? That's one time constant. When t becomes R times C, the product of RC. V naught, the Vt is going to become what? V naught e to the power negative tau over tau or negative 1. Now, calculate what e to the power negative 1 is. So this is one time constant, let's say. This is 2 time constant. This is 3 time constant. 4 time constant. What is e to the power? So when t is equal to tau, what is e to the power negative 1? 0.367. So that will make it 0.367 V naught. So at one time constant, let's say this is half V naught, and somewhere here is going to be 0.367 V naught. 0.367 V naught. At one time constant, the value of the voltage drops down to 0.367 V naught. So the official definition of the time constant is the time it is going to take for the response voltage in the capacitor, and then we're going to see the same thing for the current in the inductor. The time it is going to take for the voltage across the capacitor to drop to 36.7% of its initial voltage value, that length of time is called the time constant. So anytime someone asks you define time constant, that's the definition of time constant. That in a source-free circuit, whether it's an RC circuit or L circuit, in a source-free circuit, the time it is going to take for the energy component, whether that component is capacitor or inductor, because both store energy. The time it is going to take for the energy component to drop down to 36.7% of its initial response value, voltage or current, initial value, that time is called time constant of the circuit. That's the definition of time constant. So if you see me any class in the future, advanced classes, you're going to see me, of course, I teach advanced classes. And if I ask you, what is the time constant? Because we're going to use it in multiple classes, then make sure you give me this definition, because I know that I told you this definition. So write it down, remember this definition. The time it is going to take for the response to drop down to 36.7% of the initial response value is the time constant of the circuit. And it is always calculated from the source-free circuit. So even if you have source in the circuit, first you remove the source, make the circuit source-free, and then you calculate R times C from that source-free circuit. If there's multiple resistors, you make the combination of resistors across the capacitor, R equivalent, and then time constant is going to become R equivalent times C. And we're going to solve those problems as well. All right, what about 2 time constant? What is going to be the value at 2 time constant? E to the power negative 2t. E to the power negative 2, sorry, not 2t. E to the power negative 2. 0.1, 0.135 V naught. Okay. So this is, all right, 3t. What is the value at 3t? So observe there how fast it is going down, because it's an exponential decay. At 3, e to the power negative 3. 0.09, right? Huh? 49. Okay. So almost 0. And then of course 4t is even going to be smaller. So it's an exponential curve, as you can see. Hard for me to draw here, but and eventually, I mean, it's not going to become 0 mathematically until it will hit infinity, but usually we take about 4 time constant, maximum 5 time constant, and we say practically the response has gone down to 0, because even at 2, 3, 4, even at 4 time constant, it is 0.049. So 4.9% of the original voltage. When you calculate 5, it's going to be like 0.00 something, I don't know. So usually in 4 to 5 time constant, we assume that the response is almost dropped down to 0. And generally, when we are plotting the response, or we are calculating the response, or we are setting a circuit, we don't basically run the circuit for more than 4 to 5 time constant, because the response generally drops down to 0 by that time. Okay. Oh, it's a 3 time constant is 0.049. So 4 is going to be even smaller, and 5 is going to be even more small. Whatever the value is, doesn't really matter. So generally, what we call it, right, around 4 time constant or 5 time constant, we call it the steady state has achieved. So all the energy is dissipated from the capacitor, and now there's nothing left in the capacitor. If the capacitor is charging, we're going to discuss that when the source is there and capacitor is charging, before it starts discharging. If the capacitor is charging, again, we assume that in around 4 to 5 time constant, it is fully charged. And it will have the maximum voltage across it. Because after that, again, mathematically, it's going to be infinity. That's going to take to charge and discharge. But practically is just 4 to 5 time constant. The value is low enough such that we can ignore rest of the values. All right, let's do one problem before we take a break. So that's going to be problem number 2 for today. Okay, so you have a switch that we will assume is going to open up t is equal to 0. You have a voltage source, call it 10 volt, R1, 1K, R2, 2.2 kilo ohm, capacitor is 10 microfarad, R3 is 5.1 kilo ohms, and R4 is 6.7. Usually you can find these values of resistors, so just using some practical values. So the switch is going to open up at t is equal to 0, and we assume that the circuit has been running for a very long time before the switch is going to open up. That is, the circuit, the capacitor is going to be fully charged, and it will be at a steady state. Circuit is running for a long time before the switch will open. So if this statement is given to you, that means capacitor is fully charged. What do you have to find out? You have to calculate the value of the capacitor voltage at 0 negative. Capacitor voltage expression for t greater or equal to 0 positive. And power dissipated in R4 at t is equal to 10 milliseconds. So capacitor voltage at 0 negative means we are trying to find the initial voltage on the capacitor. That initial value is going to be used when we are writing the expression for the capacitor voltage in part 2. So that's going to be our V naught. That V naught is going to be used here in the second part when the capacitor circuit is going to become a source-free circuit. When the switch is going to open up, that means the left side of the circuit is going to be gone, and you have the right side with capacitor, R3 and R4. Those three components are going to become a source-free circuit, and capacitor is going to start discharging through R3 and R4. And then we will find out when it is discharging, what will be the power dissipated in R4 at 10 milliseconds. That is, first we're going to calculate how much current is there at 10 milliseconds, or we can calculate voltage division, how much voltage across the resistor for at 10 milliseconds, and then calculate the power dissipated in that resistor at that time. So understand the question first again before you start solving. Yes, there is. Yeah. Yeah. So VC0 negative means that switch is opening up at t is equal to 0. Just before the switch opened up, what is the voltage across capacitor? that time is 0 negative. Yeah. And then just after the switch opened up, that time is 0 positive. So that's what we represent basically before the change, right before the change, and right after the change. And change is happening at t is equal to 0. Before it opens up, yeah. 0 negative is before it opens up, and 0 positive is after it has opened up, just after that time. That's, negative and positive represent that. Okay, so before it opens up, we know that the circuit is running for a long time. That means capacitor is fully charged, which means that there is no current flowing through that branch where the capacitor is connected. So that branch is going to be considered as an open circuit. So how are we going to calculate the voltage across the capacitor in that case? Who is going to tell me? It is the same voltage that will be across R2. Okay, and how we are going to calculate the voltage across R2? Don't go to nodal or mesh analysis when you can solve using Ohm's law. Remember, the circuit is very easy, right? The circuit is 4 resistors connected with a source. So you can always apply the combination of resistors and calculate the voltage or current in any circuit. If you have just one source and multiple, yes. Huh?
Since it is closed, you can just say that it's a closed circuit.
Yeah, of course it's going to be, when the switch is closed, of course the current is flowing through this, right?
I just wanted to make sure.
I'm redrawing it. Yes, you don't have to redraw, by the way, but it is good if you redraw to show that this is the circuit before the switch opened up, t is less than 0.
Yeah.
And then the value of capacitor voltage that you're calculating is from this circuit. So that's what I'm going to do right now. So I'm redrawing the circuit. I'm going to close the switch and capacitor. This is open circuit. And then you have R3 and R4. So once you redraw the circuit, right, R2, R3, R4, R1, R2, R3, and R. Once you redraw the circuit, you can see how simple this circuit is. You're trying to figure out, of course, this is the voltage, capacitor voltage, VC, which is the same voltage across R2 or across the combination of R3 and R4. So how are you going to find VC out? What's going to tell me? Don't go into loop or node and stuff. Combine the resistors and find VC. What is the combination of resistors, and how are you going to apply that to find VC? Remember, anything that you can do with Ohm's law, don't go beyond that. There's no need to do that. Voltage division, current division, Ohm's law. Then no need to do any other thing. Okay, so what is the combination of resistors? Remember, you're trying to figure out voltage across R2. What is the combination of resistors that you can see in that circuit? Say it again. Are in series, okay? No. What? Yeah, R3, R4 series parallel with R2. And you just have to stop over there. You don't have to go beyond that, because why? Because you're trying to figure out the voltage across R2, right? So you can, once you have two resistors connected, R1 and R equivalent, then you are trying to figure out the voltage across what? R equivalent. And you can apply voltage division easily. So you don't have to, do all the way, calculate current and you can do that. It's not there's no problem with that. But if I write this down, that VC will be equal to Vs times R equivalent over R equivalent plus R1 where R equivalent is equal to R3 plus R4, which is in parallel with R2. One equation and you get VC, right? So instead of writing KVL equation, KCL equation, this and that, single equation, and you're gonna get the value of VC at t is equal to 0 negative. All right, so let's go ahead and calculate that and go and connect this to my flash drive because I have my equivalent program over there. All right. Let's see what values did I choose for everything. All right, so my Vs is 10 volt, my R1 is 1K, my R2 is 2.2K, my R3 is 5.1K, and my R4 is 6.7. 1K, 2.2, 5.1, 6.7, and 10. And capacitor is 10 microfarad. These are all the values. And then I have now R equivalent is the parallel combination of R3 plus R4 and R2. So R equivalent is 1854.3 ohms or 1.85 kilo ohms. 1.854. And our VC is equal to Vs times R equivalent divided by R1 plus R8. 6.49, approximately 6.5, 6.4965. Okay, any question, guys, about this? This is what I want you to do basically. Observe the circuit and don't jump into KCL, KVL. Observe the circuit and think how I can solve it the easiest way. And again, if you can apply Ohm's law, current division, voltage division to find whatever you're trying to find, you really don't no need to write the equation of KCL or KVL or anything. So once again, observation is important. Take a couple of minutes, observe the circuit, and then decide what is the easiest path, easiest course to go about to find the value that you're looking for. As you can see, again, I'm not stopping you to use any program. I'm using program myself because I know how to calculate the parallel combination. I'm not going to spend time to keep doing the same thing that I already know. But this is just going to make life easy, and you move on to again analyzing the circuit rather than spending time on solving the circuit. Solving is easy. Analysis is what you have to learn. All right, any question about this? This makes sense? Right? Makes sense? Okay. So this is the initial voltage that we are looking for at. So this is part one basically. Did I put part one? This is part one. So this is the initial voltage on the capacitor, which is equal to VC0 negative, or we will call it V naught. And pretty much in every problem, you will have to find the initial voltage on the capacitor before you make the circuit source free, because you need to know that voltage in order to write the equation for the voltage Vt. So now the second part, that the circuit becomes source free. So the source opens up. source-free RC circuit. So we are not concerned about the left side of the circuit anymore now. Because again, the question is asking us, what is the value of the capacitor voltage at this time? So although when the source is going to open up, there is still this circuit here. The source will still supplying current here, but we're not concerned about that. Our concern is now this circuit, C, R3, and R4. Greater or equal to 0 is fine. Don't have to put 0 positive. 0 is okay. C, R3, and R4. And this is the capacitor voltage. So we know that when you have a capacitor and you have resistors, then the capacitor voltage is going to drop in an exponential form, and that equation is pretty much a standard. VCT is equal to V naught e to the power negative t over tau. You have to figure out what tau is. So what will be the equation for tau in this circuit? Say it again. R3 plus R4, equivalent of these two, times C. Very good. So R3 plus R4 times C. So the equation of VCT in terms of math is going to be, let's calculate tau. Tau is equal to R3 plus R4 times C. 0.1180, 0.118. 0.1. That is going to be the capacitor voltage response when the switch is going to go T greater or equal to 0. All right, if you have any question, please go ahead and ask. So the time constant is what? 118 millisecond. 118 millisecond is the time constant. That time is going to take for the capacitor voltage to drop down to 36.7% of 6.5 volt. 118 millisecond. Observe that the smaller the time constant, the faster capacitor is going to discharge. And the larger the time constant, it's going to take for the capacitor to take that long of a time to discharge in the circuit. And that time constant plays a vital role when you're creating filters, RC filters, and all those things. Because you want, for example, if you remember from your semiconductor devices class, all of you have taken semiconductor, I'm assuming, right? The circuit that you built for your rectifier circuit, the half wave and full wave rectifier, all those things that you discussed, and then you put the capacitor towards the end to make the AC wave, not AC waveform, the pulsating DC waveform into kind of constant DC waveform. So basically, what you were doing, you were creating an RC circuit like this, because you had the L load connected, which was a resistor, and you were connecting a capacitor value in parallel to that. Now, the value of capacitor that you're supposed to choose is such that the time constant of the circuit RC becomes large enough, such that when the next waveform is arriving, the capacitor is still not discharged much. So if you make the time constant larger than the time period of the pulsating waveform, quite large, I would say, then the capacitor is going to hold its charge. It's going to start when the waveform is going down, it's going to start discharging, but it's going to take its time. And by the time the next waveform will arrive, it's going to start charging the capacitor again. So your capacitor voltage is going to be pretty much stand still, because output, let's say, of the full bridge rectifier is like this. And when you put a capacitor, you're creating a filter, basically this RC circuit. Let's say capacitor is charged to the maximum value, and then it starts discharging. But this RC time constant you keep to be quite large, such that when the next cycle arrives, the capacitor has not discharged much. And then it will start discharging again, and then start discharging. So basically, this pulse is going to become something like this. And then even if you make the RC time constant to be large enough such that it won't even discharge, or discharge extremely small that it's negligible until the next peak arrives, then it's going to become pretty much a constant DC waveform. So there's a whole game of the time constant over there. You're trying to find a value of capacitor such that when you multiply that value of capacitor with the load that you have connected, a load resistor, your time constant is large enough such that capacitor will hold its charge until the next waveform arrives and the capacitor starts charging again. So that's the time perspective of the filter, RC filter, that you have used basically. So they were playing with the time constant over there. Okay, let's do this thing. It's already 10:30, so let's go ahead and take a break and then solve the third part after the break and then do some more problems. Power in R4. What will be, how are we going to find out the power in R4 at, what was the time? At 10 milliseconds. What's going to tell me that? What should we do first before we calculate power? Well, find what? I'm sorry. Okay, we can do voltage division and find the voltage across R4. And once we have the voltage across R4, then of course we can find the power. That's fine. I would say since a specific time is given to us, 10 millisecond, we can just find the voltage across the capacitor at 10 millisecond, because that is, a capacitor is acting as a voltage source now. So we can find the voltage across capacitor at 10 millisecond and then apply voltage division to find the voltage across the resistor at 10 millisecond, resistor 4, and then we can find the power. So PR4 at 10 millisecond. So let's say VC 10 millisecond. Okay. So VC at 10 millisecond is going to be 6.5 VC times exponent of 10, negative 10 over half. Oh, is that small? Negative 10 millisecond. Negative 10 millisecond, exponent negative 3. 5.98, 9686. 5.96864. So we know that the voltage VC is this, which means VR4 at 10 millisecond, which will be VC at 10 millisecond times R4 over R3 plus R4, voltage division. VR4 at 10 millisecond will be VC times R4 divided by R3 plus R4, 3.389. And which will give us power in R4 at 10 millisecond is going to be VR4 at 10 millisecond square of that divided by R, V square over R. Our R4 is equal to VR4 square over R4. 1.7142 milliwatt. 1.7142 milliwatt. And again, you don't have to do 4 significant figures, just 2 of them should be good enough. 1.71 milliwatt should be good enough. All right, guys. Any question this? About this problem? Any part that is not clear? Make sure everything should be clear to you when you're doing a problem. Otherwise, you're just gonna be choosing this method, this method, this method, but you would not know what you're looking for. Things need to be very clear when you're solving something. Yeah. Well, it is from the source we're drawing because the time at which the power is required is 10 millisecond. And at that time, the circuit is going to be source free because the switch is opening at 0. So 10 millisecond is after 0, right? So it is a source free circuit.
So the reason why I'm asking is because just like previously where I talked about redrawing the circuit, I think that's what I'm studying.
We did redraw the circuit. This is a circuit, right?
No, what I'm saying is how wouldn't change it.
No, we're not changing anything. Yeah, we're not changing anything. It's still the same source free circuit. There's nothing changed in there. Yeah. Okay, guys. So I hope the problem, you understand the problem. The problems are going to be similar problems when you are calculating response, capacitor response in a source-free circuit. Orientation of resistors may be changed and all those things, but the approach is going to be the same. That is, first you calculate the voltage, initial voltage across the capacitor from the circuit, and then you use that initial voltage and whatever source-free circuit, all the resistors and stuff that you have. You create that circuit, and from that circuit, calculate the tau, the time constant. Write down the equation of the capacitor voltage for t greater than 0, and from that, you can calculate whatever you're looking for. All right, let's look at another problem. This will be our problem number 3. All right, let's see. You have Okay, now I'm going to introduce one more thing in this problem to you. This is capacitor. Let's say start from here. Let's say R1, R2, R3, R4. Let's assume this is a current source, IS, which is going to be, let's take it to be 10 milliampere. Okay, R1, 1.6 kilo ohm, R2, 2.2 kilo ohm, R3, 3.6 kilo ohm, and R4, 4.7. And capacitor we can take as 100 microfarad. Actually 10, let me rewrite the value. It's going to be 10 milliampere, but I'm going to write it down as 10 U negative T milliamp. Okay. 10 U negative T milliamp. That U that you see, anybody know what that U represents? No, it's not micro, it's U. So the U represent a unit step function. Anybody know the unit step function? Anybody? Unit step function? Anybody from other classes? Have you? Okay. Okay, so you know, anyone else? Lazaro, you know, right? Unit step. I'm just asking if you have used it in any other classes. That's what I'm asking. Yeah. Anyone else? You guys have used unit step function in any other class? No. Okay. So what is a unit step function? A unit step function in analog domain is basically a function that represent that as long as its argument, that is whatever is in the parentheses, that's called argument. As long as the argument is negative, the function is going to be 0. So if I draw a unit step function ut, as long as the argument which is in the parentheses is 0, the function is going to be 0. And when the argument is going to become positive, the function is going to have a value of 1. That's called unit step function. So for example, if I draw ut, and if this is my time scale, then the function is going to be 0 for all the negative values of time. And when this becomes 0 and positive, it is going to have the value of 1. So you have to basically analyze when this argument is going to become positive. For all those values, the system, when the argument becomes 0 or positive, for all those values, the output is going to be 1 for the unit step function. And if the argument, as long as the argument is negative, then the unit step function is going to give you a value of 0. So this is what a unit step function is. So now you can play with the argument. You can change it. For example, u t plus 4. So what do you think when this function is going to become 1 and when it will be 0? When t is negative 4, then it's going to be u0. And when t is negative 3 is going to be u1, t is negative 2, u2. So all those values that are 0 or positive, the function is going to be 1, and all those values at which the argument is negative, the value is going to be 0. So any value of t which is less than negative 4, the function is going to be 0. and all the values where you have t greater or equal to -4. So basically this function is going to be changing at t is equal to -4 from 0 to 1. So that's what unit step function means. So when we write a source in terms of unit step function, what does that represent? 10u -t. Exactly. So -t means when t, all the negative values of t, the argument is going to be positive, because negative times all the negative values of t, the argument is going to be positive. So it is going to be on, 1 is on, 0 is off. It is going to be on for all the negative values of t until t becomes 0. And for all the positive values of t, the argument is going to be negative. So the function is going to turn off. So this is basically putting a switch in series with is and opening that switch at t is equal to 0. That's what it means basically, right? For all the negative values of t, whatever you see in the parentheses, argument is going to be positive. So the value is going to be 10 milliampere, because u is going to be 1. So 10 times 1, 10 milliampere. And for all the positive values of t, the argument becomes negative, and at all those values, the system becomes 0. So this means is is on until t is equal to 0, and is becomes off after t is equal to 0. That's what it means. Say it again. It is a switch, basically. So it's acting as a switch, but we are not showing a physical switch, basically. We're just representing that switch as a unit step function. And remember, when the is going to turn off, that means is has become open circuit. Current source is going to become open circuit when it is off. Voltage source is going to become short circuit when it is on. So switch on, if I put a switch instead of unit step and I open the switch, then of course you're not going to consider this is source, because it's just going to be gone, right? So anytime is becomes 0, this means you can remove that branch. It's open circuit. Anytime vs becomes 0, you short that branch. So this is basically the story of unit step function, and that's how we use it to represent sources, to show that they're turning on or turning off at a specific instant of time. So now this is on for all the negative values of t and off for all the positive values of t. Okay, so what we have to find out? Let's say determine the first VCT for t greater or equal to 0, 0 positive, 0. I'm just going to write that down. VC, of course, is going to be voltage across capacitor. Number 2. Power in R1 at t is equal to, I'm going to decide what time we calculate power based upon the time constant. So I'm going to leave it right now and come back to it. But the first part is that we have to do, we have to write down the expression for V for t greater than 0. Okay, so now remember the steps. What is the first step when we are trying to figure out what is the value of, or what is the expression for capacitor voltage? When the change is going to happen, and change is happening, of course, at t is equal to 0. So what is the first step that you do? What we did in the last problem. Say it again, Glorian. Yes. So we find the initial value of the voltage across capacitor before the change happens, right before the change happens. So we assume again circuit is running for a very long time. Capacitor is open circuit, is fully charged, acting as an open circuit, and we find the voltage just before the change is going to happen. That is when the capacitor is fully charged, it's at a steady state. So what is the voltage across the capacitor? That's what we are going to find. Okay, so this is going to be our circuit. Now, who is going to tell me for the first part how we are going to find the voltage across the capacitor? What may be the easiest way to find the voltage across the capacitor? Remember, capacitor you assume as, when it is fully charged, you assume it's open circuit, so no current is flowing through capacitor. Okay, you can do combination of resistor, but again, look at the ultimate goal, like how you are, what is your, if you do combination of resistor and stuff, how are you going to use that combination to find the capacitor? That's what you need to think. Okay, let's do current division. That's easier. If we do current division, then we will find the current. But basically, what is we to find VC? What exactly we are looking for? That establish that first. We are looking for the voltage drop across the series combination of R1 and R2. That's the voltage across the capacitor, right? Because R1, R2 in series, they are connected in parallel with the capacitor. So we are looking for that. And we can find that voltage drop if we find the current that is passing through R1 and R2. And of course, R3 will be the same current because all of them are connected in series if the capacitor is open circuit. And to do that, we can easily find it using the current division since we know the total current. So we can apply current division and find what current is passing through those three resistors. So let's do that. Your circuit is going to be simply R1, R2, R3, R4, IS, and this is the voltage you're looking for, VC0 negative. Let's call this I1, and let's call this I2. Oh, we don't really need to find I2, but we just need to find I1. Okay, so using current division, I1 is equal to the total current, which is IS, times the equivalent of the resistors divided by R1 plus R2 plus R3. All right. What is the equivalent of resistor over here that we are referring to? Who's going to tell me that? Very good. R1 plus R2 plus R3 in parallel with R4, because that equivalent represents the parallel combination of all the resistors among which the current is dividing. So these are in series in parallel with R4. So R4 parallel R1 plus R2 plus R3 divided by R1 plus R2. And from this, we can find I1. Let's go ahead and find that. Okay, let me go ahead and plug in my values first. R1 is 1.6 K. R2 is 2.2 K. R3 is 3.6 K. R4 is 4.7 K. And IS is 10 milliampere. Okay. Let's go to that equation that we have. So now my I1 is IS times the parallel combination RP of R1 plus R2 plus R3, comma, R4. Parallel combination of those resistors divided by R1 plus R2 plus R3. 3.884 milliampere. So again, observe, if you have just that small function, just the parallel how easy it becomes. Like instead of doing in multiple lines, first calculating the equivalent and all those, you can just do everything in one line. So you don't have to worry about calculations anymore. You just have to worry about, as I said, analysis. How you're going to analyze the circuit to find what you're trying to find. Yes, Chris? You can do whatever you want. I don't really care, but what is wrong with this? Why do extra stuff when you can do things without going to extra length? That's my whole point. You can do whatever you want, but you don't need to. So why do you want to do that? All right. Question up to this point. Is that this clear? How did we find the current? And once we have the current, of course, we can calculate the voltage across the capacitor, the initial value. Therefore, VC0 negative, which is V naught, is I1 times R1 plus R2, because they are in series with each other, and that series combination is parallel to VC. V naught is equal to I1 times R1 plus R2. 14.76. This voltage is the initial value, and using this voltage, then we're going to find the expression for VC. So T. So this is basically T less than 0. We are solving for T less than 0 up to this point, and now T greater or equal to 0. Okay, so at yes, you have a question? So at T is equal to 0, of course, the source is going to disappear. That means we will be left with R2, R1 parallel with C, and that will also be parallel R3 and R4. So we have two resistors in series on each side of capacitor when the source is going to become open circuit. So let's redraw the circuit real quick. So you have R1, you have R2, you have capacitor, and then you have R3, and then you have R4. R1, R2, capacitor, R3, and that's our source free circuit. We know the equation, of course. The equation is going to be VCT is equal to V naught e to the power negative T over tau. We find V naught, we found V naught already, 14.76. Let's find tau. So who is going to tell me what would be the expression for tau? Remember, to find the expression for tau in the source free circuit, you combine all the resistors across the capacitor. So your equivalent resistance should be across the capacitor, one resistor across the capacitor. So what will be the equivalent of those four resistors across the capacitor? Very good. R1 series with R2 in parallel, and that will be parallel to R3 in series with R4. So that will be the equivalent capacitor. R1 plus R2 in parallel with R3 plus R4, and that will be multiplied by the capacitor to calculate tau. Tau will be equal to Rp, R1 plus R2 R3 plus R4 and times C. Did I put? Oh, I did not put C in my equation. Let's go ahead and do that. Okay, C is 100 micro exponent negative 6. 100 micro. Oh, I have to write this again then. Okay, so tau is, should have just run it and then had an error so that I don't have to rewrite it. Anyways, Rp R1 plus R2, R3 plus R4, and times 0.2607, 260.7 millisecond. 260.7 millisecond or 0.2607. So the expression for V is going to be 14.76 e to the power negative t 0.26 volt. That's the result of part number 1. All right, any question about this? Make sure if there's anything that is not clear, make sure you ask me. And once again, I will encourage you, if you don't, start using Octave. As you can see, it just makes life very easy as far as solution is concerned. Analysis you have to do, but solution you don't have to worry about. If you have small functions written already, like parallel, and then we're going to discuss the second order filter, you can write the functions in that as well. So all those things, you just the calculation becomes very easy, and you don't want to spend time on doing calculations. You want to spend time on, as I said, analysis and doing things right. Calculation is it's not difficult. So next part that I put, okay, so based upon the time constant 0.26, let's say we find this at 0.1 second, so that it will be less than one time constant. And that power is in R1. Power in R1 at t is equal to 0.1 second. Okay. All right. So who is going to tell me how we are going to find that? Say it again. Okay. No, but that voltage is not across resistor R1 though. Yeah. So you have to find the voltage across R1 first. Remember, you cannot just use any voltage and divide it by R1. You have to find the voltage across that resistor, square it, and then divide by R1, or you find current first that is going in that R1 and then I square R. But that's just a mistake that I've seen actually in many, many students make that mistake, that they don't take the correct voltage to calculate power. Remember, you cannot just take any voltage. It has to be the voltage across the component where you're finding the power. So first you're going to find the voltage, or you can find the value of VC at 0.1 second, because that value is going to be used as a source voltage. And then we can find, since R2 and R1 are in series and the voltage across them is VC, so we can apply voltage division on R1 and R2, find the voltage across R1, square that, divided by R1, and that would be the power in R1. Say it again. we're gonna use VC to find VR1 first, and then use that VR1 to find power. Yeah. So VR1 is equal to VR1 square over R1. You can write the equation first, that's okay. That's VR1. And VR1 we can find using VC. VC times R1 over R1 plus R2, voltage division square. This is voltage division. Divided by R. So PR1 at, what was that, 0.1 second, 0.1 second. Let's go ahead and calculate it. I'm just going to calculate everything in MATLAB and then just paste that. Okay. So T is equal to 0.1 and my PR1 is equal to let me define my VC equation quickly. VC is equal to V naught. I have V naught. So V naught times exponent of negative T over, I have tau, right? Yeah, I have tau. So that's my VC. And T is 0. So R1 is equal to VC times R1 divided by R1 plus R2 square divided by R. 0.01128 or 11.208 milliwatt. 11.208. Let me go ahead and paste that. Of course, V naught and tau, all of those in my, as you saw, all of those variables are in my octave work. So I don't have to enter the values. Tau I calculated already, V naught I calculated. So again, one thing I want to clarify, observe that I'm using Octave and MATLAB to do the calculation, but when I'm solving the problem, I'm still showing all of my steps and everything. And that's what I expect you to do, that you show the steps, you show the understanding why you are calculating what. So I'm showing all the steps, all these. Many times students, they misinterpret the work from Octave or MATLAB that, oh, this is the only thing that is required. No, that is for you to solve, that's fine, but that's not how you represent your work. You have to represent your work properly. If you want, you can paste the screenshot from your Octave, that's fine, like I'm doing it. But at least you have to show me the work that this is how you, this is the formula that you use to calculate this and all those things. All right, guys, question up to this point. Anything that is not clear? So these are source-free or natural circuit, RC, natural RC or source-free circuits, remember. We're going to discuss, of course, the forced circuits next week on Monday, in which you have the source present after the change happened at time t is equal to 0 or any time reference time. The source will still be in the circuit, or another source is going to come into the circuit or whatever. But so we're going to discuss how that source is going to, then how you're going to represent the equation of the capacitor voltage if the capacitor is not acting as a source, but there is another source. Capacitor energy is changing, because if any change is happening in the circuit, then capacitor energy level is going to go from one level to the other level. So we're going to look at then how we're going to interpret that, how we're going to calculate before the change happened, after the change happened, what will be the complete expression. That's what we're going to discuss. But we're going to do it, of course, next week, since we don't have that much time left right now. Any question that you may have from what we discussed today? I will see if I have, of course, some homework problems that I'm going to post from the capacitor basic stuff that we did, integration, differentiation, and then from the source-free circuits. I'm going to post a few problems from the source-free circuit, so make sure you work on them. There will be due, of course, next week on Wednesday, and you can expect a quiz, of course, on Wednesday, since you will be turning in the homework. I know the report is also due sometime. I forgot what is it due? Right? Okay. All right. The report. Make sure you follow the guidelines that are given in the rubric as well as the sample report, so that you don't lose points in the report when you submit. Because most of the time when I'm grading the first report, I see all sort of mistakes. People don't even look at the guidelines that I provide, and then they lose points for no reason. So make sure you don't do that. I expect that everyone finished the lab in the open lab, right? Because quite a few of you did not finish it. So make sure you don't write the report without finishing the lab. You have to finish the lab. If you have not, you go to the open lab today and then finish it, because the report is due tonight, right?